So as we did yesterday, we are recording the session. So we will post the recording in like 2-3 days on our website. So you will be able to rewatch it and share it with everyone you want. In the meantime, feel free to find your way to the question section. It's a little section of the GoToMeeting dialog, and feel free to type in hello or just type something so that I know that you can hear me and that you can see my screen properly. Great. Thanks, Hada. Awesome. Thanks. Great. Okay, let's wait like 1 or 2 minutes more because I see that people connected are still increasing. So as soon as we will reach some plateau. So I hope you enjoyed the session of yesterday, and today we will go a little bit further. There is so much that we can tell, of course, but my idea with these two sessions is to focus on very few but very important pre-processing steps. And then at the end of this session, I just want to like summarize and wrap up everything so that we will draw some conclusions. Okay, people are still connecting. For those of you who are just connected, feel free to find your way to the question section and just type in hello so that I can be sure that you can see my screen and hear my voice. And of course, you can ask question at any time, as you did yesterday. It was great because you asked a lot of questions in real time, and we were able to answer in real time. So it was funny. Okay. Okay, I think we can get started. So again, feel free to ask any question you want. Today online with me, Greg Veltri. So either me or Greg, we will answer your question in the question section. So it's the second part of this bootcamp on data preprocessing. I want to start by summarizing a little bit what we've done yesterday. So yesterday I mentioned you what I think are the rules of the game in high dimensional data analysis. Okay, you might remember like high dimensional data analysis doesn't do any magic, so don't have too much expectation. So if you don't find something that you like, it might simply be that there is nothing interesting in the data. You know, data is data, or that the high dimensional data analysis pipeline was not built and set properly. This is another possibility, of course, but this is why we are here, to learn how to do it. Then you are always the smarter guy in the room when you're running some high dimensional data analysis. So do not blindly trust in what the computer tells you. Always validate your finding, and take your time. Take your time to learn, to read, to watch video, to ask people, to ask colleagues. So high dimensional data analysis, it's a huge topic, it's a technique, and exactly as you will, you will never like learn painting in a day or skiing in a day. Well, take your time because you will probably nobody can master any technique in a day. So don't rush, step by step. And then yesterday we dedicated basically the last the last half of the section on scaling. Why scaling? Because It's probably the most important pre-processing step. Most important because basically every downstream algorithms, with very few exceptions, benefit from a scaling step. Okay, the only two exceptions that we mentioned yesterday were Flow AI and DNA cell cycle data analysis, but otherwise, like tSNE, UMAP, FlowSOM, k-means, every algorithms that rely on distances benefits from a scaling step. And today we're moving forward, and I want to present you other two important pre-processing steps, which are normalization and downsampling. And again, I want to remember, in these pre-processing bootcamp, we're not going to speak about tSNE, UMAP, SPADE, and FlowSOM, and all the other cool algorithms, because we already have a lot of material on our website, and because we already know that you are super excited by those algorithms. So we want to dedicate time to the pre-processing, because most of the time we find out that pre-processing is a little bit underestimated. Okay, so first of all, normalization. Normalization, it's a little bit like a generic term. Normalization aims to bring the parameter distributions, we will see some examples, into alignment. And why I say it's a quite generic statement, because what you are aligning, like you're aligning the distribution in terms of mean, in terms of the minimum, in terms of the maximum, in terms of the standard deviation, what you are normalizing. So in FCS Express, there are two pipeline steps that can be used to normalize the data, the parameters. One is actually called normalizations. The other one is called 0-1 scaling. Generally, yesterday we spoke about scaling, and what we wanted to do with scaling, what we do with scaling, it's making distances homogeneous, making actually the importance of distances homogeneous within a parameter. Like, remember, if you take a parameter, yesterday we used a lot the CD8 APC Cyclone 7 for one of my files, the unscaled data as the negative very compressed, the positive very broad, and what we do with scaling is to making the two peaks more homogeneous. Okay, the negative it's more broad, and the positive it's more compressed. So we are giving equal importance to the distance at the higher intensity value as compared to the distance at the lower intensity value, but we are still doing this parameter by parameter, so within parameters. Now we are doing something different. We are trying to make different parameters more homogeneous. This is why we want to somehow align them. We want to make them more homogeneous. We want to make them more comparable in terms of mean, in terms of standard deviation, in terms of minimum, in terms of maximum. Okay, so again, keep in mind this. Yesterday we were working within each parameter. Today we are working to homogenize multiple parameters. And of course, if you do this for multiple parameters and multiple files, we are also doing this for multiple files. So which are the differences? The what it's called normalization in the FCS Express pipeline, it's a step that basically divide every single value within a parameters by the standard deviation of that parameters. So at the end, after the normalization, that parameters will have a standard deviation of 1. And you can already imagine that if you do this with 2 parameters, each of them will have a standard deviation of 1. And if you do it with all parameters will have a standard deviation of 1. So you see, you are making the standard deviation homogeneous between all the parameters of interest. You can also, before dividing by the standard deviation, you can also subtract the mean. Okay, you took a parameter, and you subtract from each single cell, from each single value, the mean of that parameters. So let's do something very, very simple. Like you have 3 cells, parameter 1, and cell 1 has a value of 1, and then cell 2 has a value of 3, cell 3 has a value of 5. Okay, 1, 3, and 5. The mean is 3. Now let's subtract 3 to all of the cells. So the first one is now -2. The second one is 0. The third one, which was 5, it's 2. So now the mean is 0. So if you do this, if you do the full normalization, so you subtract the mean and you divide by the standard deviation, every parameter you selected will have a mean of 0, so it will be centered on 0, and will have a standard deviation of 1. The 0 to 1 scaling acts in a different way. It doesn't align the mean and the standard deviation, it's align the minimum and the maximum. So maybe you have a parameter that goes between 0 and 1000. After the scaling, the 0-1 scaling, it will go between 0 and 1. And another parameter that goes between 100 and 1 million, after the scaling step, will go between 0 and 1. So now you are aligning the minimum and the maximum. Again, think about the difference between what we were doing yesterday with the scaling, okay, and what we are doing today. Today, we are making parameters more homogeneous. Usually, either, let's say, the normalization and the 0-1 scaling use the scaled parameter as input. So usually, in the pipeline, in FCS Express pipeline, the normalization or the 0-1 scaling comes downstream the scaling step that we learned yesterday. So let's have a look at some parameters after the normalization, either with the normalization step or with the 0-1 scaling. And I like drawing on my screen, so let me take my highlighter. So what you see here on the left is my data set. And what you see here are the scaled parameter. Okay, this is our old friend CD8 APC67. We deal a lot with it yesterday. So these are the scale parameter. Let's have a look at those parameter. You can see here the parameter, but it doesn't really need to go into which is which. Just look at the distribution. So we have here a parameter that has quite a lot of positive cells, and we have a similar one here which has quite a lot of positive cells. Then we have, for example, this one, which has quite a lot of negative, quite a lot of negative, quite a lot of negative. And then we have a third type of parameter, which is fully positive. Okay, let's have a look at what happened when we apply the normalization. We are centering on the mean, and we are resizing the distribution so that the standard deviation is 1. And indeed, you see that before, the mean and the standard deviation were completely different, like 4, 3, 6, 2, 3, 5, whatever. Now the arithmetic mean is all 0. So they are all centered on 0, and the standard deviation is 1. So we are aligning the mean and we are aligning the spreading. We are making the spreading more homogeneous. And you can clearly see, for example, if you compare similar parameters, like remember this one and this one, now they are much more comparable. So the CD8 was more spreaded than this one. Now, if you compare this one and this one, they are much more similar. And also, if you look, for example, this guy, this guy, and this guy, you see they are not really aligned, but after the normalization, here we go. Okay, it's a way to make them more homogeneous. But you can also find something that I will define as artifact, for example, like in this case, you see this is a CD45, those are all positive in this sample. We know that those are all positive. We have some dim and some bright. Of course, these parameters, this value, are much more compressed, let's say less variable than any other parameters. It's a quite homogeneous population. Okay, yeah, we have dim and bright, but it's more compact than anything else. So the results of the normalization is that this is spread out so that, again, the standard deviation, it's 1. Okay, so there is a question in the scaled and normalization, okay, in the center, anything above 0, it's positive. Is that an accurate? No, absolutely not. So you're not saying that whatever it's above 0, it's positive, and whatever it's below 0, it's negative. Absolutely not. Okay, you are just remapping the data. This is something that also someone else asked today. You're not defining which is positive and which is negative, neither with the scaling that we saw yesterday, nor with the normalization or the 0-1 scaling. You're not defining which is which. Okay, defining which is positive and which is negative, okay, it's up to you because you know the biology. Okay, now you're just remapping, you're just translating and compressing the data to make them more comparable, parameters by parameters. And the 0-1 scaling, what you see at the right, does it in a different way. So it doesn't center the mean and doesn't make the standard deviation homogeneous. What the 0-1 scaling step it's aligns is the minimum and the maximum. You see, for example, let's have a look at this one. So the first one is CD3. Okay, because of the biology, because of the amount of antibody, because of the brightness of the channel, of the configuration of the instrument configuration, okay, this parameter has a minimum of 0 and a maximum of 6. Those are scale data, okay, 6 and 0. And then we have the CD8, okay, which has a minimum of 0.48 and a maximum of almost 9. So what you're doing here is to tell, I don't want to consider this discrepancy and I want to give them equal importance. So now the CD3 goes between 0 and 1, the CD8 goes between 0 and 1, and everything else goes between 0 and 1. So it's a way to give every single parameter the same weight, the same importance. Okay, so none of the parameters will be really a driving force, okay, in terms of separation, because distances now are more homogeneous between parameters. So there is another question. Looks like for the last one, normalization, so the 0-1 scaling, this one, reduces the heterogeneity. So this is always happening with a, let's say, higher or lower extent when you are normalizing. This is why you should do normalization with care. So it's always a balance between flattening the heterogeneity and, sorry, the technical heterogeneity, but also flattening the biological heterogeneity. So it's really a delicate and tricky steps, the normalization. So thanks for asking. Yeah, I hope I answer your question, the Bajit. So the best thing you can do is probably trying, okay, trying the normalization, try the 0-1 scaling, and see, and trying especially if you know that there is a huge and annoying batch effect in your sample. So let me move on here because this is the consideration, and thanks for anticipating. So again, the normalization align parameters to make them more homogeneous. So you're giving parameters an equal importance, okay, to overcome discrepancy. And discrepancy might be, let's say here, let's go back to this one, okay, this one versus this one. You see, this is much broader than this one. This discrepancy might be biologically relevant or not. So this is the crucial point. When you're flattening everything. So this is why here I say this should be done with care. Okay. Personally, I will say that the best way to reduce the technical variability, because what you want in the ideal world, it's reducing or eliminating the technical variability without eliminating the biological variability. But the best way to do this, to achieve this, this goal, it's working on standardizing what you do before the high dimensional data analysis. So I know this is like an effort, it's time consuming, but that's the best thing you can do to reduce, I will say, the technical variability. So standardize the sample isolation and processing, the staining protocol, like the cell concentration, antibody concentration, temperature and time, and also the acquisition. Like there are, if you ask your core facility or the representative of the instrument that you're using, they will guide you to use like rainbow beads, controls, and so on. The idea is that, for example, you want to acquire, ideally, if you acquire the same exact sample 1 day after, 1 week after, 1 year after, you should see exactly the same value after the acquisition. Okay, if the CD3 it's 10 to the 4, should be 10 to the 4 even after the acquisition, even after 1 year, right? If you run the same exact sample, ideally. So you want to flatten the technical variability, I need to work on the bench to do that. So at that point, whichever variability you will see in the data when you're doing the high dimensional data analysis will be biological, or, and that's something that you cannot avoid, will be just the variability of the fluorochrome, but at least you are reducing, right, the possibility. So you are saying, okay, I titrate my antibody, I use the same antibody, I use the same concentration. So you are limiting the variables. And at that point you say, okay, this variability is just because of the dye, and this is just because of the dye. And if I see another sample, which is here, okay, that's important. I know that this, it's biologically relevant, and I don't want to remove this variability. So you see, if you remove the technical variability, the normalization will be sometimes detrimental, sometimes useless. Okay, so what about a functional marker which typically shows mirror expression? If we change the standard deviation to normalize, are we potentially reducing the dynamic expression of Absolutely, yes. So this is exactly an example. So what you say. So this is in this case, it's CD45. Like, let's say that this is like a homogeneous peak, completely positive because it's an activation marker and we activated the cells. And in another sample, the cells are less activated and the peak is here. And in the other sample, cells are not activated and the peak is here. Okay, if you do normalization, either with the standard deviation and mean or the 0-1 normalization, those three peaks, okay, will end up to be 1, 2, and 3. Okay, so do this only if you think it's useful. Do not just do it because you think it's always useful. Sorry for the repetition. Okay, but those are exactly the question that you should ask yourself when you decide to run the normalization. Okay, I'm doing something good for my data, or I'm losing information. Can I use different normalization technique for different fluorochrome for the same sample? So mathematically speaking, you can do whatever you want. Of course, you can like scale the CD3. Sorry, you can normalize the CD3 with the normalization step and the CD4 with the 0-1 scaling. Just consider that you will end up at that point with different value, right? So if you scale the CD8 with this, okay, you see it goes minus 1.7 plus 1.7. Okay, so here you are about like 3.4. And then you scale, for example, the CD4 with the 0-1 scaling, and this goes between 0 and 1. So at that point, what you're doing, it's telling the algorithm, look, this one, it's really more important. It's like 3.4 times more important than this one. So the distances here will be larger. So in that case, you're doing something intentionally and you are, let's say, increasing the importance of a specific marker. Okay, it might be tricky, might be risky, unless you know that you really want to do that. Okay. Okay, so this is actually great because those are all really interesting questions. So let me erase a little bit. Let's go back here. So again, I want to stress the last point here. So a lot of time I'm asked, I want to run high dimensional data analysis. I have a lot of sample. We acquired the samples like in the last 5 years. And in that case, the batch effect will be, unless you did this, okay, unless you spend time to standardize everything, the batch effect will be huge, okay, and it will be hard to remove it. You might succeed in limiting it, but at that point you will probably also limiting the biological variability. So that's the counterpart.